So, hello everyone. I'm going to present the work I did together with my colleagues Maximilian Kunz, Marcel Suiker, and our professor Karsten Berns. Okay. What's the idea? So, we worked in a EU-funded project named HumanTech, and the idea was to have a remote controlled demolition scenario. The whole scenario looks like this. We had associated partners from Kajima, which were selecting, had a BIM model, where we were selecting an area which should be theoretically demolished, so like a square which should be cut out of a wall. When this information got into a task planner, it created a navigation task where a robot should drive, and when in our case, a marking task, because we were not able to put like a chainsaw on the robot, and we tried to mark the positions which the person selected in the BIM model. And what I'm going to present here is the lower part, so the navigation approach and the marking approach we did. The whole idea behind it was we wanted to utilize the information we have from the BIM model for both our localization within the building and for the navigation. So let's start with our scenario more or less. So we built a building with 3 rooms. It was roughly of size 100 square meter. And we had like 3 rooms and relatively large openings because the robot was quite big and it had to be able to drive through those openings. When the civil engineers we worked together, they created us an IFC file of that environment. And we also imported it to Unreal Engine. Since we only had roughly 3 months with a robot, we started to develop our algorithms within the simulation and later on brought them to the real robot. This is our hardware setup. So we had a robot which was built by the company Baubot. It is a differentially steered robot platform, and it was equipped with a YAS cover arm. When we had, since we didn't get any feedback from the robot arm, we had the marking tool in the front where you could put a pen inside. And if the pen is pushed into the tool, so if you have a contact to the wall, there was a sensor which is detecting that the pen is pushed into the tool. And when we got the message, so we know we finished the marking and could drive back from the wall. Our whole navigation and localization approach is based on an Auster OS1, which is a 360-degree LiDAR scanner. And as computing unit, we had an Intel NUC. So now I give an overview about our 2 main contributions, which is the localization and the navigation approach. So for the localization, we had like 2 workflows. Before going to the environment, we had the IFC model. And we extracted a 2D representation of that IFC model on a specific height. And for later on in the environment, we had a LiDAR scanner. We used mainly point cloud library to extract the corners of our rooms and the normals of the walls. And then we created also a 2D representation of our real environment. And when we matched those 2 representations, and used them to calculate the difference between our measured environment and the IFC model. One important thing to mention here is we had to know in which room we are. So we initially told the robot in which room we are starting. And while driving, we are tracking which is our current room. So we always we knew to which room we had to compare. Theoretically, that might also be possible without that prior knowledge. But that wake-up problem is a whole different topic. So let's say you are in a complete building and want to detect in which room you are. There's literature about it, and that was too much work for us to perform in that scope here. Additionally, we had issues when traveling between rooms because we have like half a scan of one room and half of a scan of another room. In that case, the matching was not possible. So we used the odometry of the robot for the localization. And as soon as we are completely in a new room and we're able to detect it again, we switched to the point cloud-based localization. So about the navigation, we used some more or less well-known algorithms from robotics. So for the navigation, we used an elastic band fusion algorithm. It's based on some pre-calculated points. So we created a grid map from our FC model. We performed the flood fill algorithm, which gives us points from our starting position to our end position. And when we used some of those points to create those bubbles for the elastic bands fusion algorithms. It works in a way that these bubbles, there are two kinds of forces which move them, which are moving those bubbles. One is a force which comes from the closest obstacle. So our target points are pushed away from our obstacles. And then there are internal forces between neighboring points, so that there's like a more or less similar distance between the points. Later on, I will also mention some slight changes we did because we had some issues using the algorithm as it is described here. Now about our experiments. Sound. Yeah. Can I mute it? Okay, then I will do it anyways. So we had two kinds of experiments. One was in a simulated environment, which is here shown on the left. The other one is the real robot, which is doing some noise at the moment. So first about the simulated experiments. This one here shows some of the first tests we did with the elastic band fusion algorithm. Here we had some problems with the bubbles which are created because sometimes they were really close, and we had like a really simple navigation approach, which is just rotating to the next bubble and then drives forward while correcting a bit if it's a bit off of the target point. And here we had the issues that the robot was strangely rotating between the points because we had too many of those bubble points. So later on in the real experiments, we used some fixed bubbles within so we forced to have fixed bubbles within the rooms, and we massively reduced the number of bubbles we had for our algorithm. Maybe we'll skip this and continue with a real experiment. So this is how it looked in the end. So we had 4 times the actual speed. We had always like 1 or 2 points within each room, and we had fixed points in the doorways between the rooms. So here the robot is completely autonomously navigating until it reaches its target position, and when we switch to the arm control and we calculate the local position for the arm where it should drive, then it moves slowly towards the wall. Our main issue here is, since we don't really use any vision sensors for the arm, we had to have like a quite big safety distance, and we are slowly moving towards the wall until we get the contact signal of our marking tool. So it took quite long from moving in front of the wall until we were able to mark the position. And in a second you can see now we have the contact to the wall, and then the arm is moving back to the position where it started to mark and continues with the next position. And then that's the second position, and then it would continue to drive again and mark the other 2 points of the square which was selected. Now to conclude, we demonstrated how to use typical robotic applications utilizing the information we get from BIM models. We used like quite simple sensor setups, so only a LiDAR sensor and the inertial measurements from the robot. We utilized the BIM models for planning algorithm and for the localization. For the planning stuff and navigation, it worked really good. The localization was quite inaccurate in some cases. So sometimes we didn't manage to get a decent localization within, especially the big room, which causes problems when placing in front of a room, and also leads to a quite bad position, which was sometimes at like 5 to 10 centimeters. The worst cases, it was almost 50 centimeters off of the actual target we had. Here on the right, you see some failed tries where yeah, we had one big issue in the corner here, so we were sometimes hitting the wall, sometimes we had to stop it here. That's also like an issue of inaccurate positioning, because we couldn't see in front with a LiDAR scanner because there was the arm in the way. So we couldn't always avoid, we were not always able to successfully drive through the building. So that's it from my side. Here are my contact information. Thank you.